Hello, everyone, and thank you for joining us for another session in our 2021 Climate Action webinar series. My name is Suyama Bodhinayaka. I'm the Director of Advocacy and Sustainability at AIA Orange County, and I will be your moderator for today's webinar. As you know, AIA California has developed an in-depth series focused on understanding, implementing the AIA Framework for Design Excellence. This series has offered 27 webinars so far this year. As always, all webinar content and additional resources will be available on the AIA California website shortly after each session. Additionally, more information on the final climate action webinar for the year will be shared in your follow-up email. A few quick housekeeping reminders before we get started. Please use the Q&A function to ask any questions for today's presenters. You can also like a question to move it up to the top of the queue. Now to today's webinar. Today's session qualifies for 1.5 AIA HSW learning units for those watching live, and AIA California staff will report these units for you. The session is also being recorded and will be posted on the AIA California website with additional resources and a PDF of the presentation shortly after today's session. This program will examine the process and the decision-making that led to an all-electric approach at the new University of California Irvine Medical Center, Irvine, UCIMCI Design Build project. This project is located on a pristine site adjacent to a large wetland marsh and includes a 144-bed hospital and an ambulatory care center, a shared surgery suite, and outdoor venues. Sustainability and a connection to nature are core design principles, coupled with an understanding that these connections lead to wellness and a better patient outcomes. Now, I would like to quickly introduce you to today's presenters. Brian Pratt, AIA, DBIA, AUA, Lead AP, is the campus architect and campus architect and associate vice chancellor for design and construction services at the University of California, Irvine. Currently overseeing all major academic building projects, he leads the design and construction efforts for the campus, delivering highly complex projects via design build. In his more than 7-year tenure at UCI, Brian has overseen several project types, including research facilities, laboratories, active learning classrooms, dormitories, and highly technical projects. He has worked on the private and public sectors and served on the board of directors as the president of the American Institute of Architects, Orange County. Brian is accustomed to working with complex projects and multiple user groups, and his work has been recognized with several awards and recognitions. With sustainability as a priority, many of his projects have achieved LEED Platinum certification. Tom Chessum, FAIA, is an established health architecture planning and design innovator, leading high-profile and complex projects with a responsive style that creates holistic, integrative solutions. Over 40 years, he has led the planning, programming, and design of healthcare environments that unify institutional vision and mission with the commitment to improve patient and staff experience and their safety, operational efficiency, and resiliency. His experience ranges from prestigious bioscience projects such as the Salk Institute's East Building to comprehensive healthcare projects for UCI, UCLA, UCSD Health, Paloma Health, City of Hope, Kaiser Permanente, and in Southern California. Tom speaks to and writes for national clients and professional forums. His projects have been published nationally and have generated national awards from modern architecture, from modern healthcare, healthcare design, ENR, and the AIA. Tom is a principal at Co-Architects and has joined the firm in 1986 as one of its original members. James Wahlmeier, PE Lead AP, is a principal engineer and design and construction services at the University of California, Irvine. James provides support on project programming, design build drawing reviews, energy calculations, construction support and commissioning, and lead pursuits. Now I would like to hand over to Brian to lead the presentation. Brian.
Thanks, Yama. Good afternoon, everybody. Tom's going to share his screen here and we'll get going. Okay, so this is a view from the marsh of the new project, and we'll talk in detail about it, but this gives you a sense of scale. Go ahead, Tom. So Yama covered the learning objectives. We're going to talk to you a little bit about process, but hopefully do a real deep dive into some of the decision-making surrounding the University of California Irvine Medical Center Irvine project, and some of the considerations for all electric central utility plant humidification and sterilization uses. Go ahead, Tom. Okay, a little bit about the project background. This team, we are really fortunate to have a partnership of several team members. Go ahead, Tom. So the project is being run by the University of California Irvine, my group, and the primary stakeholder is UC Irvine Health. You can see on the right here the team. This project is a progressive design build approach that employed a two-step process for selection of the design build team. We hosted a RFQ, a qualifications pre-qual, that shortlisted to 2 teams that then competed in a proof of concept design competition that also included some validation of cost models, communication of how team members communicate among design considerations and system considerations. And then we awarded based on a technical score of the conceptual design combined with a cost component, which was basically general conditions, overhead, and profit. The project was not bid at award. After award, we worked through a design development kind of phase, a schematic design development kind of phase, and worked towards a guaranteed maximum price, which allowed for great input from our UC Irvine Health partners. Our typical design build approach is a lump sum design build approach where there is a design competition, including a formal complete bid. And we didn't see that that could be conducive to a hospital project because the hospital project, there's a degree of complexity that involves a lot of stakeholders, surgeons, physicians, nurses, administrative folks. So the progressive design build approach allowed us to bring in some detailed input after award, but before signing of the GMP. Now, we perceived some risk between award and GMP that cost fluctuations could be in play and have a serious impact on scope. So in advance of award, we spent about a year with HOK doing a fully detailed project program to really be able to communicate the vision as well as the criteria around which the buildings would be designed. And we think that that work coupled with really tailoring the general conditions for a progressive design build project mitigated our owner's risk from award to the signature of the GMP, so that it narrowed the variability of scope and cost constraints in a way that helped us get to a GMP quickly, and a GMP that actually was very close to our target cost. Our target cost was $717 million, and our GMP through added scope and such came to $727 million. So incrementally, a very minor uptick, relatively speaking, considering the added scope that we included. So once again, we're so fortunate to have a really great team. We really consider everybody on this screen as a partner to contributing to the success of this project. Go ahead, Tom. So the project goals are really driven by what a patient experiences and the factors that contribute to that patient experience. And so the patient experience is enhanced by operational excellence But as Suyama mentioned, this site is on the border of the San Joaquin Marsh. And it's really a one-of-a-kind location and contributes to wellness and respite, and provides for a natural environment with views from the beds and the infusion suites and so on. And so, we consider these as the touchstones of the project, but sustainability for UCI has always been a priority, and I'll get to that later. But this project is no different. Sustainability from the outset was really a fundamental project goal, and we'll get into a lot of the detail about that. But nonetheless, we're really proud to have sustainability be a priority of ours and something that we value. And really, value is the key to us. You need to balance what you value, and sustainability, along with patient experience, operational excellence, and the marsh, are all demonstrative of what UCI values in this project. Go ahead, Tom. So sustainability doesn't come just out of the blue here. Back in mid-2020, the University of California Office of the President published a policy on sustainable practices, and it really challenges the campuses to provide highly sustainable projects, including all electric projects. It's a comprehensive system, and recognizes all independent and interacting subsystems or elements. It needs to be cost beneficial, but energy conservation and sustainability has moved to the forefront of projects across the UC system. And in order to get any kind of latitude when it comes to this policy, if you can't comply with the policy, you got to go through a waiver process, which is really quite challenging. The University Office of the President takes this policy very seriously and expects that the campuses will not only comply, but raise the bar when it comes to sustainability for the UC system. Go ahead, Tom. So a little bit about the project. We have about 580,000 gross square feet of building in this project. The hospital is 144 inpatient beds, an emergency department. And something pretty unique is the inpatient beds are standardized as ICU beds, so they can be fully converted over time for full ICU use. There's inpatient surgery, a PACU, prep and recovery. So the hospital itself, as you can see here, is about 357,000 square feet. The image on the right shows the emergency department in the bottom right and the entry to the hospital on the left-hand side. Go ahead, Tom. So the Comprehensive Cancer and Ambulatory Care Center is another about 223,000 gross square feet of the 580, and it includes primarily cancer-focused functionality, cancer center, breast center, outpatient surgery, PACU, radiation oncology, infusion suites, and so on. One thing that Tom will get to is some of the unique connections below this plaza level that connect the ambulatory care center and the hospital project is a shared surgery platform. But this is, one of the primary outpatient centers. Go ahead, Tom. So this gives an overview of the project. In the in the far right, there's our Center for Advanced Care and Parking Structure, which is another project, a medical office building and urgent care. In the center of this picture is the parking structure in the drop-off plaza. And then bottom left is the ambulatory care center, and top left is the hospital, the acute care hospital. And you can start to see on this image how the marsh becomes really a part of our project, and we think is something that really makes this site special. Go ahead, Tom. So just to try to orient you a little bit, the site is on the corner of Jamboree and Birch, very close to Jamboree and Campus. From Jamboree and Campus on west to our site is what UCI calls the North Campus. And the North Campus is currently houses most of our facilities management functions. And it is divided from the main campus by the San Joaquin Marsh and University Drive. So we're kind of right in the center of a lot of intersections of major byways and highways. And that was part of the thinking about the origins of this project, is that, you know, UCI has our project, our hospital in Orange, but we felt that we needed to get closer to this area in order to serve South Orange County and Coastal Orange County. Because as you know, driving the 55, trying to get to Orange almost any time of the day anymore really takes a lot of time. And so this site really presented itself as a real central opportunity to provide and reach out to the broader community. The bottom right here just shows you a sort of some of the texture of the marsh and what a rich environment it is. And we've been working with the UCI biologists and ecologists on how to delicately live next to the marsh, as well as to support some of their research functions within the marsh itself. Go ahead, Tom. So on the left-hand side, you can see kind of a map here of the functions of the UCI campus. In magenta in the upper left is the new site. Right sort of dead center in the middle is the green section, which is Aldrich Park, which is the park around which the whole campus is planned. You can see in the middle picture pedestrian trails and a local regional trail system that links us all the way up to the North Campus through a Naturescape wellness trail. We can connect up in hiking trails all the way to Bomber Canyon directly from the campus. And then on the right-hand side is really just a map of open space with Aldrich Park in the middle and the San Joaquin Marsh in the upper left. Go ahead, Tom. So the Naturescape program is an initiative that the campus has embarked on to provide a lot of these linkages through gardens and pathways across the campus. And you can see in the upper left-hand side there, we intend there to be a really direct connection, pedestrian and bike connection from the campus across San Diego Creek and up to the North Campus, in the hopes that people will use this as a wellness trail, not only to get to functions at the hospital and connect the hospital back to the Health Sciences District at UCI, but also just as a really terrific place to go and hang out and experience the marsh. Go ahead, Tom. So LEED is, of course, an important measure for UCI, and we are proud to be tracking for LEED Platinum on the hospital project for healthcare, LEED for healthcare. It's certainly a challenge, but we do believe that LEED is a pretty good metric to measure sustainability. It's not the only metric, of course, and you know, the bar is being raised on other aspects of sustainability that LEED perhaps doesn't address, but it is a good measure, and we're tracking towards platinum. We hope to achieve it and expect to achieve it, and this team has been very innovative in not only meeting the campus criteria, but finding other ways to enhance the LEED performance. Go ahead, Tom. So the ACC, the Ambulatory Care Center, and Parking Garage and Central Utility Plan is tracking for LEED Gold. You can see trending up towards platinum, but we are solidly in the gold. And once again, you know, thanks to some real terrific collaboration among the design team and the owner group. prioritizing and valuing what it means to achieve LEED Gold and Platinum and a high degree of sustainability. Go ahead, Tom. So as a hospital, this is an OSHPD project, which is now called the HCAI. That requires a real tremendous amount of agency review and collaboration and coordination and incremental reviews with the HCAI. And that really becomes kind of the critical path for the project. And we do various segments. I think there are 5 increments with several segments in each that lead us through the approval process. So there's an overlay here that is, unique for a hospital project. For UCI, we are our own jurisdiction, and but for a hospital project, we are not. So HCAI takes on the regulatory responsibilities. Go ahead, Tom. So Tom's going to take you through some of the thinking surrounding the planning and the design of the project. And then we'll get into some of the nitty-gritty about some of the engineering and all electric aspects.
Thank you, Brian. Good afternoon, everybody. I'd like to continue on the track that Brian has started here and just giving some context to the project and to basically understand the overall scope and picture that the sustainability, zero carbon, and energy exists in. Really, with healthcare, we're balancing a lot of issues, and I think Brian put an important word out there, which is balance. We're talking about patients, we're talking about operations, we're talking about the lifespan of the building, and what we're targeting here is that this is a building that at minimum has a 70-year lifespan. We're looking at the project conditions, and in this case, the time and place of the project is very important. And certainly cost and life cycle cost comes into the picture. So coming back to talking in the project itself, Brian has introduced the pieces and parts. And the biggest story here to some extent is how this facility positions itself between 2 worlds in multiple senses. It's between the natural world and it's between the city, between the urban world. But it's also between what traditionally we call the town and gown. We're very much centered between the edge, or sitting on the edge of the academic world, but also into the community. And with that comes many other features of the facility. It's not only healthcare, it's research. It's not only those two, it's also education. And that just brings a richness into the project that is underlies everything we do, even to the extent of thinking about energy and all-electric approach. So I like the idea about the harmony. What we're after here, when we look at the extent of the marsh, and we think about that open space, and we also think about the position of the facility, it's really achieving a harmony. It's a harmony between its location, its need for access, all the things that come along with a healthcare facility, but all the things that also come along with being at that edge and location within a community. We're dealing with patient healing. We're dealing with staff. We're dealing with the recruiting and retention of staff. All of the function that goes with the hospital, from loading docks to oxygen storage, to fire access. In this location, very, very large issue related to water treatment. How can we actually support the marsh as water comes through from a stormwater perspective, it is treated and released into the marsh. And then looking at the image to the right, the enlarged site plan, accessibility is really the key here. It's really the important thing about a patient's experience. Having a simple approach from Jamboree without any kind of decision-making, being able to find the drop-off and the access to whether it's the hospital or the ACC or the parking structure, all of it very tightly knit. Traditionally, I would say if we were to be putting this much program on a site, we would almost want twice the amount of site, but that has been achieved here in recognition of the location in something that's probably half the size of what we would normally look for, but it's densified. Underneath the drop-off plaza is also parking structure. Underneath the plaza between the hospital and the ACC is the primary surgical platform. The plaza itself between the two buildings really becomes an outdoor space, a functional part of everything that goes on in this location. And then accessibility is a really critical part of what we're enabling here with this location. And to the lower right, below the ACC, there is a ramping system that provides universal accessibility to the marsh through sloping of the building itself, you know, kind of terracing, stepping down, as well as bringing a ramping down into the Naturescape walk, which comes directly in contact to the hospital and the ACC. So I'm going to walk quickly through the building itself so you have a sense of its scale and content. This is everything that goes on in a hospital and everything that goes on in really a higher end outpatient facility. The plaza, again, in the middle is very much the heart of the facility. It's both the place for privacy, for respite, for patient families to get away when they need that kind of time, but it's also a place of celebration. This is a teaching facility. There are events that go with that, graduations or white coat events. And the goal is to be able to center these buildings around those kinds of operations and to very much respect and take advantage of the climate and the temperate climate that occurs in this area. Very much warm suns, light breezes for the most part, so that outdoor space becomes really a huge asset, especially when we think about such things as what we're experiencing today with COVID and the ability to break out, be outdoors, and expand space. So on this floor, the hospital's to the left, the outpatient facilities to the right. Flanking the plaza are public spaces on both sides, public lobbies, all the public assets, whether it's gift shops, cafes, conference rooms, education facilities coming down towards the marsh. So just looking at that in perspective, looking from the drop-off plaza, what we're really talking about here is, again, establishing that kind of relationship that has that kind of longevity of that 70-year building. And that goes to materials, and it also goes to how everything is assembled together. And while we look at the pictures here, I want to divert a little bit into two items, one being the structural system. UCI has taken a perspective on resilience that suggested that a brace frame approach was preferred. That has been shown to provide the most simple response to a post-earthquake, let's say, possible damage conditions or repair. We looked further at that also from the perspective of embodied carbon and found that the buckling restrained brace frames, which you can see some to the left here in the ACC, actually resulted in a structure that was about 20% less than any others in terms of embodied carbon. So there was kind of a double win there. Certainly a criteria from UCLA, but understanding the double win of the embodied carbon within the structure. The second part is the building enclosure. It's a unitized exterior curtain wall system, glass and metal panels. One of the criteria we've worked with on the fabricator of that is that every element, though unitized and standardized, is also customized to its condition. Looking to, at the end of this, use the least amount of material and in a sense, the carbon embodiment of that element of construction. What it comes down to, though, in all of this is the relationships of the parts, addressing the needs of the people, the patients, the staff, the students, bringing them in contact with, daily contact with both sides of this world. In the section at the bottom, there's a kind of simple explanation of how the street edge comes into the plaza, parking structure in the middle, parking structure below the plaza. There's also a drop-off and pickup bay right to the right of directly to the right of the hospital, basically to give patients very discreet access post procedures, and also basically to give staff direct and simple access into the facility. But all of that cascades down and opens up into the marsh on the far left, with situations such as the upper right image of the cafe dining terrace, which essentially opens up over the marsh. What we call the marsh level, because it's not a basement, it basically opens on three sides to the marsh, is the interventional platform. 25 different kinds of procedure and interventional or surgery rooms, all in one operational unit. There is a kind of fissure that you see through the middle of this plan, which is the separation between the OSHPOD 3, or I guess call it today HCI 3, outpatient facility on the right, and the hospital on the left. The intention is that these work seamlessly, but then we do need to basically bring together the regulatory requirements of how these separate. And in the upper right corner is the drop-off that I mentioned, coming down to the marsh level and giving access to these facilities for patient convenience. From the other side, we're really looking at a kind of scalar response to the marsh. Buildings, plaza, stepping down to the marsh. In the foreground is the ramping system, bringing the accessible access down to and from the Naturescape. And then clustered in to the far right is opportunities for waiting, outdoor waiting for the surgical services, or in another case, staff lounges and staff break. So again, looking at that section on the lower portion, these facilities such as surgical waiting in the upper left basically open up to the marsh, to the views, to that kind of experience where if somebody needs to spend 6 to 8 hours here waiting for their loved one, they have opportunities to get in and out. They have opportunities to move up to the plaza, to the cafes, but basically it's a day experience. Or for staff on the right-hand side, that they have the ability to have respite, decompress, get away from it a little bit, but also participate in the special character of this location. Moving up the building, on the left, the hospital, functions that usually, often in hospitals end up in basements, such as the kitchen, the clinical lab, the pharmacies, the respiratory therapy resource areas, those things like this. Decision here was people work here. They all need daylight. And then on the right-hand side is clinic areas, cancer clinics, with patient waiting and access on the left-hand side facing the plaza, and the provider work areas and really research type functions along the right side, looking out towards the marsh in that direction. So the idea of all of these is to optimize the opportunity for daylight and the opportunities for view. And lastly, moving up to the upper floors, the left-hand side is the hospital. I'll talk a little further about what Brian mentioned about the intensive care units and the approach to a standardized patient bed and unit configuration. On the right-hand side it's an infusion floor, which is, again, it's a day-long patient experience, giving them view, daylight, and access to outdoor terraces overlooking the marsh. And just before I get into talking about a little more detail in terms of the energy and sustainability features, wanted to take a quick look at the central plant. We'll come back to this when we're talking more detail about the kind of technologies here, but just giving a little perspective of how this central plant is different. It looks very much the same. It's different primarily in the proportions of the equipment that we would normally see in a central plant. And I'll just point that out because it will be relevant later as we kind of talk through the actual engineering side of this. There are no boilers. First thing, that's pretty straightforward. Everything is electric, and everything is about heat pumps, heat recovery. Those are really the unique aspects of this central plant. The air source heat pump is probably the biggest element that is unique to going all electric and brings with it some really particular kinds of challenges. It's noisy. It needs to be outdoors. It creates the demand for a lot more outdoor space than maybe typical central plants have had before. The other proportionate things, if you look at the upper level here, there's very few cooling towers. That heat is being reused, so there's less of that. But to the right of that, there's a lot more emergency generators because this hospital and the ACC need to continue to function in a power outage. And all that dependency on electric service drives up the number of elements there. So just a little perspective on the kind of changes we're seeing in the configuration. So let's talk a little bit about the actual approach to the energy here. And what I want to start with is really a body of work that UCI has built over almost 20 years related and are captured in what are called the campus standards and design criteria. But it's a body of work that really lays out a foundation to put a building in a good state from the beginning in terms of its design approach. And I'm going to focus on really the solar aspect of this and the exterior wall and shading, and pull out a couple things here that are laid out. One being effectively prevent 85% of direct sun across the 365-day cycle. And as following on and working down the page, I think what we came to understand how valuable this foundation was is its definition of how to achieve that. A definition that has to do with not only devices or technology, but a recognition of seasonal differences, as well as exposures or orientations, and how all of that can be brought together to evaluate and meet the goals of this design criteria. In the middle, it mentions clear glass with high visible light transmittance. There are other criteria that provides minimal or requirements for minimal amounts of windows or openings to solids. Initially, they seem fairly straightforward, but it's actually very interesting that 40% of to have 40% of windows on a building is actually quite high. We've been able to get over 50 in these facilities, but it actually becomes quite a challenge when you consider also the solar side of this. And to talk about that, again, coming back to the idea of harmonizing. Optimizing for solar and optimizing for view are two really different things here, but they needed to be reconciled. How to provide view for the maximal amount of patient experiences within the buildings, both buildings, was a whole source of study in terms of how to orient and configure the building to take advantage of that marsh view and to give everybody as much, call it an equality of view or an opportunity for view as possible, but to balance that with the solar aspects of this and how to get both to work together. The studies also became about how can we self-shade? How can one building shade the other building? Because again, when we come back to that 85 percentile approach to solar gain, shading from the adjoining building becomes an aspect of that. So you can see that in that diagram that in the lower floors of the ACC, the hospital is actually helping by shading it. So positioning the buildings to help each other became a very important part. But then actually breaking that down into a room by room kind of evaluation. And we looked at different aspects of this, and I'm kind of walking through process here because it really helps describe how we work our way towards these goals to meet this criteria. On the right-hand side, one of the first things we looked at was something like the Okalux types of products. If we're going to need to deal with view and also sun control, should we go that far? On the left, more looking at the actual use of horizontal overhangs, or call it sunshades. And a quick study of that in terms of load reductions, we actually found that the horizontal overhang was more effective at load reduction, but also just from an experiential point of view, was certainly preferable when we started talking about patient experience and view. With that in mind, we took that further to start looking at how do we actually now achieve that 85% solar reduction. And that's really, again, it's a combination. It's a combination of the technology of the glass in the lower right-hand corner. We worked our way towards a glass that had a visible light transmittance of almost 50% and a solar heat gain coefficient of 0.23. That became kind of our starting place as we worked our way up and down what you could afford, what would give the best results. And then began introducing shading devices at different heights, whether at a 12-foot height, a 9-foot height, a depth of anything from 0 to 6 feet. And what we found is that the highest utility of shading device really occurred within the first 2 to 3 feet of that device. And it certainly was benefited by its location on that opening. So that became a building block of how we looked forward and really built this into a combination approach of shading devices and shading via glass technology. So in this little isometric to the left, the upper floors of the hospital utilize horizontal shades or eyebrows, projections. The lower floors utilize, and I'll show you more details of this, basically frit patterns on the number 2 surface of the glass, resulting in the same reduction towards that 85% solar gain reduction. The other thing that kind of played into this, and I bring up this detail only from the perspective that everything comes in combinations, or when multiple things become solved. A concern we certainly have in this facility and its location on the marsh is bird safety. This was brought to our attention through the biologists and the ecologists that Brian mentioned, and working with them through the details of the marsh. And it largely has to do with lower level windows that reflect greenscape, windows that could be misinterpreted by a bird at a lower level for actually being an opening. So there's kind of a double win in how we responded to that, in that the lower levels are pretty simple. And I'll get into their configurations, but the use of the frit becomes also a bird safety response, while the upper levels have enough definition to them, and they're separated from the ground plane to the extent that there is less of an issue to a misunderstanding of what an obstacle might be. So what we came up with was really a combined or a combination shading approach. The use of a frit, of a density and a pattern and an amount that would give us, in combination with the glass, the shading coefficient we're looking for, and the use of horizontal eyebrows. The largest one is 3 feet, and then there's an upper one that's 1'4", both as a light reflectance shelf, but also as a shading device for the overall window. And just to give you some images of how this feels, basically, the use of frit is largely applied to, call it the ground level or plaza level, the active areas where people are moving, people are coming and going. It has, with the cafe, the coming and going, the meeting rooms, the elevator lobbies, the lobbies, where there's not a lot of time spent. And it was felt that that kind of openness and less complicated approach to the glazing system would be opportune there, while in the upper floors, where there is more respite and more time spent in a single location, we open the windows up by using the sun shading devices, the eyebrows, which really then gives that space a much greater access to view, but the same performance in terms of the solar shading. And a final aspect before we go into the details of the all-electric, just wanted to touch on HVAC systems and the selection of HVAC systems. One of the major drivers, certainly for power demand and the kind of loads that go with it, and certainly with the heating and cooling, is the system design. We worked through 4 different systems. We worked through a multitude of their features and pros and cons. And to some extent, what it came down to was weighing the points rather than counting the points. And what I mean by that is one of the criteria, which has to do with the standardized ICU room, pretty much said that that second column, universal design and airflow flexibility, became the ace. We had to have the greatest flexibility there in the right system to really achieve that. And to some extent, despite the points that accumulate across the other issues, that became the deciding factor with the HVAC system. And the applicability to that really comes down to the developing a system that over time, while initial design is all to an ICU air change and a performance level, also has a built-in ability to change over time through basically use change kinds of permits with HCI that would not require construction, simply changes in how the controls are used to allow the building to operationalize decisions about how many ICU rooms they would want versus how many med-surg rooms. This also gives them, in the diversity of the whole system, the ability to respond to specialty needs. For instance, as a cancer hospital, a bone marrow transplant is one whole major unit. In bone marrow transplant, the air change rates are 12. ICUs are 6, med-surg are 2. But within the diversity of the system, we can actually provide that 12, a level of 12, 8 air change rate in that bone marrow transplant program. So what this has done is it's really built in the kinds of, call it resilience, that the facility needs to address all the kinds of demands that will come at it over its lifetime. So that takes us to now starting to really dive into kind of the bottom line here of the all electric design. And I'm going to turn it back over to Brian as we get there.
Thanks, Tom. Go ahead and advance the slide. So thinking about all electric systems had a humble beginning for UCI, and that's at our Anza Borrego Desert Research Station. We used heat pumps that are commercial grade packaged equipment that's readily available, and it resulted in lower construction costs because it eliminated the need for underground piping distribution to 3 separate buildings. And part of the consideration was that there might be a higher energy operating cost, but the project uses solar PV arrays to offset some annual energy costs. This is a LEED Gold and represents, really some of the start of the thinking of all electric for UCI buildings. Go ahead to the next slide, Tom. This project is our first large-scale all-electric building. This is our continuing education building here on the campus. And this is about a 70,000 square foot cast-in-place concrete building. We delivered this design build. Hathaway Dinwiddie with LMN were the architects and design build team. This project is outside of the campus core, and therefore it's beyond the district cooling and heating system distribution that we benefit from on the main campus. And we evaluated the cost of extending campus utilities to the building site, but the cost was prohibitive. So we went for a detailed project program criteria that outlined a very high efficiency standalone building. The construction cost was actually pretty comparable to a gas electric system. It's a VRF system, a variable refrigerant flow, and has distributed refrigerant piping in lieu of duct mains and risers. No vertical shafts or fire smokers for this system, fire smoke dampers for this system. The classroom heat pump air handlers are only slightly more expensive than conventional HVAC, and there are no gas-fired water heaters or boilers, no site or building gas piping distributions. And we've learned that operating costs are lower than a gas electric design due to the simultaneous heating and cooling capability of the VRF heat pump system. And the classroom heat pump operation only uses the heating mode on the coldest days of the year. Go ahead, Tom. So as I mentioned earlier, LEED is a important measure for UCI, but we also think of it as a progression. You can see that there are several LEED Gold projects, and then followed by a development of LEED Platinum projects over the years, 21 LEED Platinums with several underway. But the sort of the fifth column there, the Title 24 column, shows you percentages that we beat Title 24 by, and you can see those percentages really gradually increasing. But the highlighted portions are some of the all-electric projects on campus, and we're programmed for 4 out of the 5 bottom projects are programmed with heat recovery chillers to serve as the heating source for the building and domestic hot water. And as we mentioned, the hospital is all electric except with gas-fired kitchen equipment for meal preparation. Go ahead, Tom. So the new UC policy is, as I mentioned earlier, pretty direct. You can see the quote from the policy on the right-hand side. But in advance of that, the UC system studied the long-term 20-year life cycle of all electric versus gas electric, and came to the conclusion that all electric buildings are comparable or slightly less expensive than gas and electric over a 20-year lifespan. As Tom mentioned earlier, we're building these buildings for 70-year operation or more. So the life cycle cost gets better and better, as you might imagine. So they studied 3 building types: academic, residential, and laboratory. And we've gotten sort of challenged here and there by our colleagues in the industry about whether the construction cost assessment of the study is spot on. But as we've moved through these projects, we've learned that in fact it's probably pretty accurate. And so the essence of the new policy is that natural gas cannot be used for building and domestic water heating unless the new building is connected to an existing central utility plant. And so in our case, the hospital is not connected to our campus central utility plant. Instead, it has its own, which leads us to the next slide. So the all-electric central utility plant, you can see on the left-hand side a conventional central plant, and then on the right-hand side, the all-electric. So, the goal is to omit conventional central plant natural gas reliance. And the all-electric design introduces 2 types of chillers: a heat recovery chiller plus air source heat pump chiller to replace the conventional gas-fired boilers that Tom was noting in his earlier comments. So the chillers reject their heat into the building heating system instead of sending it to conventional cooling towers. And so the third hospital chiller on the top is a conventional high performance chiller connected to a cooling tower, serves the high summer cooling load requirements in the new hospital complex. Electric steam humidifiers replaces the conventional gas-fired steam boiler typically found in hospitals, and electric steam generators integral to autoclaves replaces the conventional gas-fired steam boiler source. Those last 2 points, the humidifiers and the autoclave steam generators, was really a hot topic of conversation because that sort of was an even higher threshold to try to accommodate in this new hospital project. Go ahead, Tom. So this slide shows a typical air-cooled HVAC unit diagram, capturing heat and discharging it to the atmosphere. And the temperature of the compressor may be in the range of 150 to 200 degrees. And with the all-electric era coming, more heat recovery equipment options are becoming available to capture and reuse this heat instead of rejecting heat to the ambient air. Go ahead. So on the left-hand side, you can see that we're going to 95 degrees. On the right-hand side, we're going to 125 degrees, and the heat recovery chiller has a higher lift and increases energy output. So the conventional heat chiller has a lift of 55 degrees, while the lift of the heat recovery chiller is 85. Now, the higher lift of the heat recovery chiller means it must perform more work to meet the lift. Therefore, the heat recovery chiller at 125 degrees Fahrenheit operating temperature does use more energy, but the 125 degree temperature can be used as hospital heating supply system. While the 95 degree Fahrenheit cooling tower is more efficient, the temperature is too low to use as a useful heating source. Go ahead, Tom. So the energy input for 125 degrees condensing water is fairly steep. It's 32%. But we think that we'll tell you why that works in a few slides here, but we wanted to acknowledge that in fact, that higher lift to 125 degrees does require more energy. Go ahead, Tom. Now, kind of an aside here, we looked at several ways to control Legionella in our domestic water system. And in order to handle Legionella, you have to consider 4 ways of doing it. Storing domestic water above 140 degrees, using ozone, using monochloramine, or copper silver ionization. And for years, the 140 degree Fahrenheit storage temperature has been the default method, but that would result in a very inefficient heat recovery chiller operation requiring excessive electrical power input. So we went with the monochloramine, but the main point here is that chemical treatment of Legionella, as a matter of fact, is actually a low energy option as opposed to the energy it takes to store water above 140 degrees. Go ahead, Tom. So this is an important slide from what we were talking about before, where the power input for the recovery chiller is actually greater than the conventional chiller, but the useful output is much, much greater. And that's what this slide is trying to show. The coefficient of performance, the COP means higher energy efficiency. And when we have heat recovery chillers with a high COP, it includes both the cooling and the heating energy. And in the COP for heat pumps in mid-Southern California climate, rule of thumb is about 3, 1 unit of energy input and 3 units of energy output. And this little picture here just shows the ductwork to outside ambient air, and we've used that style successfully. Go ahead, Tom. So the upper left shows a conventional chiller with a cooling tower, handles heavy cooling loads. Below that are the heat recovery chillers. The air source heat pump chillers provide heating water in the winter when chilled water demand is low. The chillers are robust, reliable, redundant, and the design build team has put a lot of effort into coming up with this design approach. Go ahead, Tom. So the two condenser chiller design, there's a newer chiller design that has one condenser for cooling tower conventional operation and a second condenser for heat recovery operation. And we're just using this to show that some new equipment designs are becoming available. And, you know, Tom kind of mentioned this earlier, that we feel this project is not only the right place, being in the marsh and in this location for serving clients, but it's the right time in terms of technology and the available equipment to make this all electric design become more feasible, more cost effective. Go ahead, Tom. So we're looking at energy use intensity, or EUI, in this slide, and it's represented by an annual energy use per square foot in thousands of BTUs per square foot, or KBTUs per square foot per year. There's the site EUI is the building energy, and then the source EUI is the total energy, including the central utility plant. So the top table are the DOE benchmarks, and the proposed EUI numbers are lower than the DOE benchmarks as depicted below, and meet the UC sustainability policy targets. And carbon reduction number of 530 tons is a preliminary number, but we're developing it, but that's about where we are now. Go ahead, Tom. So this slide is a EPA conversion factor table, and it shows carbon emission conversion factors for different regions across the US. And California has the best conversion factor of 0.453 pounds of CO2 per 1,000 kilowatt hours. The average conversion factor for the US is 0.884. And these factors are multiplied by the building kilowatts to hours savings to determine the building carbon reduction. So what this slide is really showing is this factor in the first column and how it compares. As you might notice, a couple, 2, 3, or 4 lines down from the red box is Oahu at 1,000, almost 1,700. So California is really quite efficient in terms of its conversion factor. Go ahead, Tom. So a UCI professor, Professor Silverman, published a carbon emission conversion factors for California utilities, which are depicted here. And the factors vary by the amount of clean energy sources that a given utility has. So a building's specific location and utility can affect its carbon reduction calculations. And we're just trying to show that, you know, depending on where you are and who you're served by, it affects your pounds of CO2 per kilowatt hour. Go ahead, Tom. Okay, so this slide here is really kind of a editorial. UCI was at the forefront of identifying ozone depletion of CFC refrigerants and propellants through the UCI professors Molina and Rowland, and for which they received the 1995 Nobel Peace Prize for their work in the 70s. UCI Chancellor Cicerone was also the head of the National Academy of Sciences for 11 years, where he influenced regulations and provided independent scientific advice to the nation. And the UC system has benefited greatly from its atmospheric policies by its own industry leaders. And, you know, we'll sort of leave you with this quote on the right. You know, we are facing this quote really quite head on. And, you know, we are really flooded by data that shows what the outcome of not doing what we should be doing might result in. And this is really just saying, look, faced with all this data, what are we going to do about it? And we think that we're making strides in getting to you know, a response to what all these predictions are saying. Go ahead, Tom. So with that, we have a number of questions showing up in the chat, and hopefully we can get Jim Wahlmeier to be able to chime in on some of these too. I don't think Jim can see them, but maybe we'll start with one that just showed up in the chat. And Tom, you might be able to answer this. What has been your greatest challenge regarding HCI/OSHPD approvals with this cutting edge design?
We're working through HCI right now. I think the primary issues we faced is how to have a OSHPD 1 facility. I'm going to stick with OSHPD rather than HCI. I'm not quite used to it yet. OSHPD 1 facility and OSHPD 3 facility on the same plant. Very early on, we determined that it was a more efficient plant if we could have a single source of, call it energy utilization on the campus that both facilities could use. But that does present certain concerns within HCI about basically protecting the OSHPD 1 side of the facility from what could happen in the OSHPD 3 side, either during a seismic event, since it's not designed at the same level. We've been able to work through that pretty well. It's all about controls and a certain amount of separation of the systems. But that's about the extent of it. Otherwise, it is pretty much for them business as usual. Yeah, and Tom, if I could, Jim Wahlmeier, good afternoon, everybody. If I could add to that, that's a great question. So OSHPD, one of the first things that they looked at when we were looking at the mechanical site plans, and as Tom was saying, putting in controls to isolate. So what they did is they had the underground tunnel, the distribution from the CUP or the central utility plant, and that utility tunnel feeds the hospital system. And then right before the utilities enter into the hospital, there's the branch piping. And that branch piping would then go over to the OSHPD 3 clinic. And I'm struggling with the HCI because when I go and read the code book, it says OSHPD. So forgive me if I mix them up here in this. But it's something we're dealing with, learning. But anyway, so at that juncture, when the chilled water, as an example, goes into the hospital, there's valves. But then when it branches off to the clinic, the first thing that OSHPD wanted to see was, okay, do we have shut-off valves there? And we spent a lot of time, working on that, thinking, should those valves, to shut down the, the heating water distribution, or to shut down, if it's a soft water system, whatever it would be, how do you take the OSHPD 3 offline? So you have an emergency, the OSHPD 1 needs to stay up, and we're going to take the OSHPD 3 building down. So it's really strategizing, as Tom was saying, and putting in those controls. And really what it amounted to for us was putting in some very high quality shutoff valves. So now we have a central plant that serves 2 buildings, and we have all of the shutoff valves in place so that we can do a manual isolation. But it was interesting because we looked at it and we were thinking, I wonder if we should do these with automation. So if there is an emergency condition, the staff, the UCI staff, the boiler plant operators, but we'll have to take that, we'll have to rename them. They can't be boiler plant operators now. They're going to have to be heat recovery chiller operators with the all electric design. But we were trying to figure out, should we set them up with automation so that they could automatically isolate the OSHPD 3 building, or should we just keep it as a manual? And the nice layout of the central plant, you have a walkable tunnel with these utilities. And I think the consensus on the medical center facility staff, they said, this is really a great design because if something happens, they need to take the OSHPD 3 building offline. All they really need to do is go from their office, run down this tunnel,
And, you know, it's real practical. Right before it goes into the hospital, they can isolate the OSHPOD 3. But, you know, it was a great question because in the first meetings, OSHPOD, they wanted to see all these details. How are we going to accomplish that?
I've got another question for the panelists. How do you address emergency power, backup power?
So on the backup power, as Tom mentioned, you know, if on the roof of the central utility plant with a cup, there's quite a bit of area for the generators. And essentially, what happened in the programming of this project was the medical center decided that they wanted to use what they call a business as usual approach. And so what that means is in a utility outage, so if Southern California Edison Power fails, they want the generators to come on and they want the building to operate as usual, as it normally would. So there's a very robust, very large generator plant, and it's actually designed to carry the entire hospital. So it kind of exceeds all the codes. And also, as Tom was mentioning, because of the all-electric design, there was some concern. So we ended up with 4 very large generators. Ends up that there's a 12 megawatt backup generator plant, and it's 4 individual 3 megawatt generators, and they serve as, you know, the backup for all of the code required systems. But then it goes a little bit above and beyond to get what the medical center staff referred to as business as usual. So this is, it's a larger generator plant than what was built into the first hospital the new Douglas Hospital that we built 15, 18 years ago in Orange. But it's kind of a nice design because it's only 4 units, whereas oftentimes you see, you know, smaller generators. And the way that they configured this, it was 4 building blocks. And the thought is that one of those generators is actually excess capacity or standby capacity. So in the event that in an emergency, you have the generators, and you know, you always have that fear, you know, when you're operating a medical center, that your generator doesn't start, you know. So this one is the standby. The fourth one is the standby. But overall, it's just a very robust design that Design Builder has come up with on this. So we're very pleased with, you know, the capacity that's built into the system. They did an air study to look at the emissions from the generators, how that might affect the air handling units at the main hospital. And then they also looked at the noise. And you know, as Brian and Tom were explaining that, you know, the placement of this property and its adjacencies, there's some residential high-rise. And so one of the things that the Coe and Hensel Phelps team did was they looked at, you know, how they can handle the generator emissions, and they looked at how they can mitigate the sound.
Thank you, Jim. There are a few more questions on the Q&A. One of them is, have you considered the local temperature effects on the air-cooled heat pumps, excessive heat in summer and excessive cooling in winter?
Yeah, that's a great question. You know, as Brian was sharing, with the heat pumps for Southern California, a heat pump typically will have a COP in the ballpark of around 3. And, you know, the question is saying, hey, what about in wintertime? So in wintertime, the outside air, the ambient air, in the design, I think, for this project is 39 degrees is the ambient winter design. But let's say it drops, and it does every year. You know, you're going to have a few days when you're, you know, possibly 33 degrees, 34 degrees. And, you know, you're relying on the heat pump as your primary source of heating, you know, for hot water distribution through the hospital, you know, for this patient care facility. So when Tom was talking about, you know, the layout, these things want to be outdoors. There's more space on the second level of the cup because of the quantity and the sizes of the heat pumps. And the nice thing about this particular design that they came up with is they're modular units. And these heat pumps, they can also serve as air-cooled chillers, and they can also serve as a 4-pipe full heat recovery chiller. So it's kind of, this particular product that they propose, it's kind of like the Swiss Army knife of chillers, but its primary role is, you know, as an air source heat pump. So in the question, you know, did we consider the outside air? And that's a great question, because, you know, oftentimes, especially on a hospital facility, you know, you take a look at, you know, your ambient design conditions, and, you know, we say, okay, we're going to operate at 39, we're going to have adequate heating. Well, what happens when you have those rare days, and let's say it goes down to 33? Suddenly, the efficiency of the heat pump, you know, it's really working hard now. There's less heat in the ambient air. So the COP in the coldest days of the winter suddenly might drop from 3, might go all the way down to 2.5. So it's drawing more electrical power to produce the same amount of heat. And the way that we've addressed it is, you know, there's redundant units, so that there's additional units. And then in the summertime, the thought is that the large conventional chillers connected to the cooling towers, as Brian was saying, that those are the summertime workhorses. So when the hospital complex has a large summer cooling demand, you know, we would use the more efficient chillers. So we don't think that the air source heat pumps chillers would really operate that much in the summer. But the nice thing about this design, and, you know, as Brian was saying, it's robust, it's reliable, and it's redundant. The nice thing about these air source heat pumps is they can serve as backups. So we have a backup conventional centrifugal chiller, but then all of these heat recovery chillers out on this deck, they also serve as backup to the primary conventional chillers. So it's a wonderful design. And, you know, one of the things when you're operating, I always think of the building engineer. You know, he's standing on the loading dock, and, you know, it's December 6th, it's cold, and he begins to sweat. Do we have enough heat? Do we have enough heat? So that was something that we worked with the design builders on, and they came back with, I think it's just a fantastic design, you know, having 3 types of chillers. And I think they've covered all the bases and provided the extra units so that in those really cold days, there'll still be enough heating to, you know, keep all of these patients happy.
Thank you, James. There's another question. Was the entire design team under one roof when the design was conceived?
You want to answer that, Tom?
Well, the truth is, given the state of the pandemic at that point, we were all under one Zoom meeting for sure. We spent Zoom and different methods of communication became our big room. And I would, you know, maybe Brian could have some points on that, but it became quite a exercise in understanding how we could benefit from that. You know, it could have been a detriment. I think the benefit is we could really all be together more than even if we were able to be physically together in various work sessions. So it had its advantages, and it certainly had its challenges too. But Brian, I don't know if you have other observations you could make on that.
Well, I would just expand on it to say we, you know, do intend to co-locate on the job site for construction. That will include representatives from UCI and the design team and the construction team, of course. So, you know, we have this terrific opportunity to leverage what we've learned about the technology and tools like we're using today, coupled with the tried and true co-location and the ability to, get up from your desk and walk over and ask somebody a question rather than firing off an RFI or a cryptic email. So, over time, we, even through the selection process, we're largely on Zoom, and that presented some challenges, but as Tom points out, some opportunities.
Thank you. There's a two-part question. One is a question about use of smart glass. Did the team consider using smart glass on the project? And the other one is part of that is the fritting. The lower levels have had fritting on the glass, and there's a question saying penetration factors of 85% of reduction in the heat gain. Also, fritting is known to create uncomfortable glare for interior spaces. Was that consideration in the application of the interior spaces? So, like, if you want to expand on that, Tom or Brian or Jim?
I'll start. Yes, we did consider the smart glass. I think couple of the features that we were concerned about in that was it does limit visibility, and it does limit visible light transmittance. It was very important, especially on that, call it grade or plaza of adjacent spaces, to have as much transparency as possible, to really have an indoor-outdoor feel. And we felt that the smart glass would really restrict that or change that character. With regard to the fritting, what we're using is a dot matrix of a ceramic frit, and basically calibrating the amount of frit to balance or achieve, in combination with the performance of the glass itself, that level of shading for that 85% target. So it actually would reduce glare just because it is a solid ceramic frit, and it has, depending where it's used, it either has some spacing variation, or there's, as you saw, there's some kind of patterning of it that we use just so that it is kind of simple to view.
Okay. Is there any specific issues with OSHPD projects for using all electric systems?
I don't know, Jim, do you want to answer that? We have not run into anything that from, call it a code perspective, that said an all electric system would not meet it. Jim described the e-power side of the whole thing. Obviously that is, gas-fired generators. There's not much opportunity to change that, but no, we have not. Jim, do you have other thoughts on that?
Yes. That's a great question. Some of our consultants have asked us that question. As we were in the programming phase, some of the consultants were talking about OSHPD requirements. They typically would require that you provide a redundant backup source of heating. So if you have the primary boiler, you would need a backup boiler, for the OSHPD 1 facilities. And I think the way that some of the code language is actually written, it almost sounds like it could be interpreted as more of a prescriptive requirement. So, the heating equipment, or I think maybe years ago, it actually said boilers. And I think nowadays it says heating equipment. But anyway, we had consultants asking us that question, hey, are you sure OSHPD is going to be okay with this? And it came up many times over several months during the programming phases. And we checked, and we really felt that what they were really looking for, or what they were going to be looking for, is as Brian was saying, the 3 R's, robust, reliable, and redundant, to have that backup so that, the goal, of OSHPD or HCI is really, they want to make sure that, the patient experience and, the hospital stays up and running and you don't have an issue based on a mechanical failure. So what we've done, we're very close. We're very far down the line on the central utility plan check with HCI. And, we're getting close to the very end of that. And there really hasn't been any questions from them saying, hey, the all electric is, we don't like it, or we haven't heard anything like that. So we're green lighted. And like I said, we're getting very close to the end of the central utility plan review. But it's a great question. And I think the thought is that years ago, the OSHPD 1 criteria within the code, it may have used the word boiler, that you have to have a backup boiler. And I think when we checked it, it was more, your heating system had to have that reliability. So I think we have all of the important ingredients, to, being a responsible design and meeting the overall intent of the reliability from HCI.
Thank you, Jim. I think we are almost at time. So last question, are there environmental health and safety issues such as sterilization, autoclaves, etc., that came up?
Jim, I think that's you too.
Yeah, so I really can't think of any. There has been some discussion on the autoclaves, whether it's electric source or steam source. But I think that we do enough electric autoclaves at the UCI campus that there's a great deal of comfort within certain parts of the environmental health and safety department. From the UCI side, and then from the OSHPD side, they're looking at it as just can we get this autoclave equipment up and running, and we have a standby unit. So I don't know that there's really a concern, because the electric autoclaves, it's not really a new product. They're very well established in the industry, and I think that the overall reliability and in long-term success of different central sterilization areas. But it's a good question, because it is a little bit new to go electric in a hospital environment. But we haven't really hit any speed bumps on this particular subject. We're trying to make sure that we hit all of the requirements, all of the health and safety requirements, and
well, I want to thank all three of you, Brian, Tom, and Jim, for that amazing and excellent informative presentation. For those who have made it so far, AIA California staff will submit your AIA CE credits. This should appear on your transcript in a few weeks. As always, more resources and tools can be found on AIA California's website, aiacalifornia.org/climate action/. More details of the remaining 2021 Climate Action webinar series will be shared to you via email. Thank you again for joining us today, and we hope to see you on our next Climate Action webinar. Enjoy the rest of your day. Thank you all.